So implicit differentiation is going to have to be used. Why? There's both x's and y's. Is this an equation where y could be solved for? If you're saying yes, tell me how. Okay. Ooh. Divide by x. Why should you never divide by a variable in your solving process? It's like a big no-no in mathematics. Why? What happens if x is 0? Then you've just divided by 0. So we don't want to take that chance in our solving process. Okay, if we're going to restrict our domain, that's fine, but right now we're really just solving, right? We don't want to do that. Even if I divide it by x, that mixture is still going to be there, isn't it? And the fact that I have a y squared and a y means the only way to solve it is through factoring. And I don't even know if this is factorable. Probably not. Okay, so because I can't solve for y, I can't make my derivative process easier, which means I have to go to implicit differentiation, right? And what rule would we have to use in here? Why? X times y. So hopefully if you did that, you winded up getting a dy dx equal to, what was it?
4 minus y over x minus 2y.
Very nice. Did we get that? Okay, very good. Good job. Okay, so we got that. So we know how to go forward quite easily. But if I asked you to take that 4 minus y over x minus 2y, and go back to the original function with through integration, right? That's how we undo differentiation, is integration. Could we do that? Could we start here and get back here? Or I'll even be nice and start with a more simple equation. Let's say we had dy dx equal to how could I get back to my original equation?
Can you take the antiderivative?
Okay, how? Every integral that we have done, and I'm going to go back to that integration by parts thing. We've had something like this. Let's say that was part of our integration by parts. Okay. We would integrate both sides. What would we get on the left? Why? Okay. Because this right there tells us our variable of integration, right? So I know that I'm going to get back a b, correct? This tells me I'm going to integrate with respect to x, right? So I'm going to get back something like x squared plus c, right? Okay. This is good because it matches everything, right? This is good because it kind of matches everything. And that's a big part of integration, is making sure that what variable we're taking with derivative or integral with respect to is a variable that comes in as an output. Everybody agree? So with this knowledge, how would I get back to my original? I know I'm going to have to integrate because this is a derivative. How would I go about starting to separate everything? Okay, that would be a good way to start. Okay. Is this okay? So I can integrate as is? The problem is, in this equation, I'm saying that y is a variable, right? I'm also saying that x is a variable. The biggest problem is that mixture right there. Okay. This is actually a differential equation, because it's a derivative, a differential equation that does not have an antiderivative, or that cannot be found by using traditional methods. So how do we determine the characteristics of the main function when we can't find the main function? How do I figure out what this function would look like if I only have this? And that is the ultimate question. Because I may not need the function. I maybe just need some characteristic of the function, whether my function is increasing, decreasing at a certain point, right? Where the possibilities of my function are going to be. Correct? So how would I go about doing that? We go about doing that by what we call a slope field. A slope field, sometimes called a vector field if you're in physics, okay, is just a field of slopes. Slope field is a field of slopes. The field being our xy axis. You guys hopefully at one point in your life have watched the news. Hopefully. As being people of that voting age, hopefully you've watched the news before. Hopefully, or you're just like every other American that just picks a button. Okay? Well, that was very political. I'm sorry. I will scratch that on this video. That was very bad of me. This is why I don't put comments on my videos. At some point, hopefully you have watched weather. Has everybody in here watched the weather at some point on the news?
Yes.
Okay. At one point in the weather, they start talking about wind patterns. The little arrows. And they are things that, like little marks that move left or right, depending on which way the wind is going, right? Okay, and it's a whole bunch of them on a field, correct? That is what we call a slope field. Okay, so you guys have seen a slope field before. Did you know that meteorology is a mathematics? Huh? Yeah, because what do they track with weather? How weather is changing. What measures change?
Like the rate at which it changes.
Oh God, that was the wrong way. That was a bad effect. What represents change? That's why there's a lot of calculus in weather, because they calculate change, how things are changing. Okay, meteorology is the study of weather. Yes.
That's a weird. I just think of
What?
Earlier we were describing the wind patterns and stuff. She goes, watch, it's gonna be a slope field. And when you go slope, she goes, bam.
Good job. Okay, so that's what we call a slope field, guys. It's about looking at the habits of change to determine what things are going to be, an accumulation of some sort. Okay, so to create a slope field, to start determining things about functions that we can't integrate, sometimes functions that we can, but we need more information. Okay, we can start to build what our function could look like. Because our general solution, from day one, when we started integration and we got our general solution, we wind up getting something like that, our general solution, correct? And I said, this tells us the characteristic of our function without telling us the location. Does everybody remember me saying that? Okay, what determines location?
C.
The Z, right? This term determines the characteristic, but the C is what helps us determine location. And we're going to see that today as part of these slope fields, because we're starting with the derivative, which is what we did in that case, right? We started with the derivative, we antiderivative, derived. That was terrible. Oh my God, I am a math teacher. I have credentials, I promise.
Oh.
Okay, we took the antiderivative, we integrated, and we got back to the function, right? Okay, well, we're going to start at the same place. We're going to start with our derivative and look to see about our characteristic without the location. And that's kind of what a slope field does. It gives us the characteristic of our graph without the location. Okay, so we can start to make assumptions about things. I do not know what I'm doing today. Okay, so the biggest thing about slope field is knowing what your dy dx is. Most of the time, that's, well, not most of the time, all the time that would be given to you. Knowing what our derivative is. Because what does our derivative represent? Slope. We need to remember that. That's slope, which is why we use it to find a slope field. Makes sense, right? If I have the slope, I can find the field of slopes. Now we're going to be looking at various points on our graph to determine what our slope would be at that specific point. Because that's another thing we know about derivatives, right? It's the rate of change at a specific time. And at every single x value, it changes, right? With the exception of one function. Which function is that? What function is the only function where the rate of change doesn't change? A line, linear function, right? Yes, everybody agree? But for every other function at every single point, that rate of change changes. So we're going to use that knowledge to create a field of slopes. Okay, we're going to start off with some easy ones, and then we'll get to some more complicated ones as we get used to it. Ones that we can find. So, a derivative can come in all types of forms. It can come in terms of x, it can come in terms of y, it can even come in terms of x and y, like our formula. Okay. So, depending on what it's like is how I'm going to kind of approach. So this derivative is in terms of x alone, right? Okay, so really, I just need the x values. I don't need any other values, just x's. Okay. I was like, you got the secret passes.
Yes.
Okay. So I'm looking at my graph. I'm looking at my x's because my derivative is in terms of x's alone. Is everybody with me? I know that is very exciting because she's getting ready to leave. What was that all about?
I just feel like that's cool, man. Like doing so many things is really
I need another volunteer. Do you want to come too?
Do you want to go?
What was that?
He needs to stay in class today. Okay. Okay, so because this derivative is in terms of x's alone, I only care about my x value. So I'm looking at my chart. For every little tick mark, I'm going to put a slope at that tick mark. Okay? For every particular point that is indicated, I'm going to put what the slope should be at that specific point. Because I only need x's, I'm only going to worry about my x-axis. Where does my x-axis start on here? It's on your graph. Oh.
Uh-oh.
Yeah. Thank you. Today's not your week.
Okay.
Okay. I'm sorry. I'm gonna have to redo this video.
Today's not your week.
So -2, where does it go? What's my index value? 2. So I'm only caring about every value, and it's only the whole values. I'm not going to do fractional values because that would be ugly. But I'm going to create a chart. Okay, I'm going to use a chart if it's in terms of x only, if it's in terms of y only. When it's in terms of x and y, we're going to approach it a little bit differently. But a chart is a really good thing. Okay, and what I want to know is what is the slope when my x is -2, -1, 0, 1, and 2. And I'm going to go back to my original differential equation. my derivative. So what is the slope when x is -2? I just plug in, right? So take -2 and plug it into the equation, I should get -3. Okay, so at any time my x is -2, my slope is going to be -3. Okay. If my x is -1, my slope would be 0, 1, and 2. Okay, so I know anytime my x is 0, this is going to be my slope. Anytime x is 1, this is going to be my slope. What I'm going to do is I'm going to create little tick marks to represent that slope to kind of get me organized. Okay, once I get used to this, I'm no longer going to have to do this. Okay, I start with the zeros. When I have a slope of 0, what kind of line would that be? Horizontal. I'm going to draw just a small tick mark, a small dash that would represent that slope, a 0 slope. How about when my slope is 1? It's almost like a perfect diagonal, isn't it? -1, perfect diagonal on the opposite, right? How about -2? So it's more steeper, right, than this one, okay? So I'm gonna go a little bit more steep. And they don't have to be exact. This is a sketch, okay? And then how about -3? Even more steep. That's okay. Don't do it straight, because if it's vertical, what does that mean?
Undefined.
It's undefined. And that's going to be very, very important for us. Okay, so what I'm going to do is I'm going to take those tick marks that I've kind of set up for myself, and anytime my x is -2, I'm going to draw that type of tick mark at that point. So at -2, I'm going to draw a tick mark on that. Okay. Well, if that's the case, at every single point here, isn't my x -2? So that means that every single tick mark, I'm drawing the same type of slope. That was not close, it's almost there. Okay? When x is -1, my slope is a little less steep, isn't it? So -1 is here. That's like almost. Then at 0, I'm at that perfect. When x is 1, my slope is 0. So anytime my x is 1, which is at every single point along there, I get that type of slope. And then of course at 2, so this is a slope field, like the weather patterns, except on the weather they're moving, because as time moves they move too, right? Okay? But we're not taking time into consideration. And what this does for us, this gives us the shape of our graph without giving us a location. So if I follow my slope fields, I kind of get an indication of what that shape is going to be like. What does it look like graphically? Quadratic. But doesn't that make sense? Because what happens when I integrate x? I get an x squared, don't I? So it makes sense that my slopes are going to follow that quadratic motion because of what my antiderivative could be. Correct? Now, this gives us our characteristic without giving us the location of where our graph truly is. In order to find that C value, what did you need? Do you remember? So if we got that as our antiderivative, how did we go about solving for C? we needed a point, an x and a y that was directly on our function, didn't we? Okay, so if I give a point, and you might want to take a highlighter out for this next part. If I have a point, I can actually sketch out my exact function without ever taking the antiderivative. Okay, so if my point is at 2, negative 1, I'm going to make sure that point is indicated on my graph. So I'm usually going to make that a little bit bigger. I got that point from here, at the bottom of that question. Okay. If my point is at 2, negative 1, I can sketch out my function by following my slopes. That doesn't mean you have to go directly through your slopes. You just have to follow them. This is a sketch. And what I mean by that, at this point it's going to be pretty close, but it's going to start getting steeper. I do not want it to be a straight line. Why did you do that? I hate my highlighter right now. Okay. Yes, you use a highlighter. I don't know why it's making my highlighter straight. Need to go check my. Okay. And I know it's going to start getting steeper because it's going to have the same characteristics on the left as the right, correct? I know it's going to come down, it's going to flatten out, and then it's going to go up. Okay. This is a sketch. This is what my exact function would look like without ever finding my exact function. Okay? That's not how you saw it? With a sketch, AP grading. They're not going to judge, they're not going to take out a ruler and measure your slope fields. Okay? What they're going to look for, and this is what I would look for when I'm grading you guys as well. Do you have your 0 slopes where they should be? Because that's an easy one to check. Check. Is there any undefined slopes, and are they where they should be? This doesn't have any. You have no undefined slopes. Check. Okay. Are the positive slopes where they should be? On this side. Check. Are the negative slopes where they should be? Check. And the answer to that, if I get a check for all 4 of those things, I got credit for that slope field. I'm looking for zeros, undefines, positives, and negatives. I'm never going to judge your slope fields because even mine are a little bit off. Okay? This is a sketch. Now another question, they could ask you to sketch out your solution curve. 2 things they're going to look for. 1, does it go through the point indicated? Which is why I make that point really large. Okay? And do they follow the slopes? If they do, you're good. Okay? Because all we're doing is we're using the slopes to determine what our function would look like. And this can be done on any derivative, whether we can integrate it or not. Which means we can start to assume different things about our function based on what our slopes are doing. Does that make sense? Okay. So on the one beneath this, what do we notice about our differential equation? It's in terms of y only, right? Oh wait, I want to bring something to life. Because it's going to be important in a minute. If we're consistent up and down, and this is true for any slope field. Okay, what I mean is every slope is the same going up and going down. Okay. This means that your derivative is in terms of x. Okay. Sorry. So what I want you guys to do this is only in terms of y, right? So what do you think the consistency is going to look like? Left to right? I would think so, since all the y's are the same left to right, correct? So I'm only worried about my y values here. So where am I going to start my table at? Probably start at -2, because we usually do tables least to greatest, right? So -2 to 2, right? And again, I only care about the whole numbers. I don't care. We tend to not do fractions here. That would be really ugly. So you're welcome. Okay, what I want you to do is to figure out your dy dx, and I want you to plot your sketch or your slope field. Yeah, because a slope is a slope no matter what variables you're doing it with respect to. I mean, and technically, that just means our x was a constant in the original equation. There's no x in it. So the derivative left it out. Okay. Yeah, so the derivative is always dy over dx no matter what form you're doing, and it's always the same no matter what variable you're doing with respect to. And from polar and parametric, that's also true. Because in polar we use r and theta, but our derivative is still dy dx. Right? In parametric, we have x, y, and t, but our derivative is still dy dx. Because that's the true derivative, no matter what. Sorry. Today's gonna be a better day. Yesterday was a weird day. Today's gonna be a better day. Whenever I have zeros or undefined on my axes, I tend to put them a little bit above or a little bit below so that I can see them, especially if I'm using pencil on black ink. Good? So we definitely got the curvature of our graph. Can anybody tell me what this graph would look like? Or what kind of graph do you think we're dealing with? Anybody can tell me. I will totally give you like 3 pieces of candy. That's how important this
Is it
graph
like
is.
piecewise?
Hmm?
Does it look like piecewise? That's what.
You
looks like.
don't get piecewise as a result of these. I guess you
I tried.
could.
Because I was thinking, because it looks kind of like
No.
it's going.
It's worth 3 pieces of candy. There are no hints involved.
Take
It
one
looks like-
and,
Okay, so I'll take 1 candy huff. Okay. 2, it's one of the most important graphs that we've talked about in here. This is an exponential. Okay, very good. So you get 2 points. And I bought starters.
Did you guys dig down in there?
So you have to dig down. I put old candy on top. What's that? Like that. Good job.
Oh, use this brown. How are you
I
gonna do
didn't-
this to your children?
Okay, first of all, do you know what the shelf stand for candy is? It's like in the years, like 3 years. You know what Hershey's and they do when they don't sell all their Valentine stuff, right? They repackage and they send it out the next year. So don't ever buy candy when it's first put out. Yes. It's work for Walmart. Their shipping department. Okay. Okay. So -2, +1 is our point. Get the crayon again. Let's use a funny.
Did you say a funny?
Okay. So at -2, +1, I'm gonna put a point.
Oh,
Said a funny one.
so it was like a funny. Okay, that's.
Because
Oh, was it colored in
Okay.
blue?
because of the zeros on the x-axis, that's your horizontal asymptote. Okay, if you think about it, right? Which means our graph is going to start to level out as it gets closer to the x-axis, right? And then it's going to start to increase when it goes in the other direction. So level out, increase. That's pretty. That made me happy. Okay.
Go back to what?
Go back to what? So let's think about this logic, because part of the solving process, if we were to truly solve this, we have to do something called separation of variables, which means I would have to get all my y's on one side, all of my x's on the other side. Okay? Well, that would mean dividing out by y, wouldn't it? Yes. What's the integral of 1 over y? ln of y, the natural log of y. And then because we solve for y, we have to do the inverse of that, which is an exponential, which is why this graph is exponential. Okay, and you guys will see that next week. Okay. Now the hardest of all of the types of slope fields is when we have a slope field that is in terms of x and y. Oh, were we right about the consistency? Being left to right? Okay, so if we have a slope field that's consistent left to right, that means we're in terms of y only. Okay. When it's all crazy and there's no consistency, that means we're in terms of x and y. Okay, so that's kind of, although I would really like for you guys to have one of these questions because it's usually one of the easier questions, but we haven't seen a slope field on the BC exam for a couple of years. Where your slope fields are going to show up is in your multiple choice. That's usually where they're at for the BC. And it's usually like matching a graph. There was one on last year's exam. Yes, one. Yes, they use a crazy one. And we're going to see a crazy one right here. Because we have a differential equation in terms of x and y. When it's in terms of x and y, I don't go to the table because then I have to make a table for x's and y's, and then it's messy. And there's a lot of points that we have to take into consideration. So what I start to look at is there any x or y value that could cause this to be 0? Or actually be undefined. Let's start with undefined. Okay. Well, if y equals 0, that means our dy dx is undefined, correct? Which means I have a slope of that. So I'm looking at the relationship between x and y at this point. And I'm going to start with my undefined. I'm going to go to my zeros, and then we'll go from there to see what we need. So anytime y is equal to 0, my slope is undefined. Is everybody good? Mm-hmm. So anytime y is equal to 0, my slope is undefined. And I'm going to put as I go. Undefineds come first. If my x and my y is not. Y being 0 is already covered. That means my dy dx would be equal to what? 0 as well. Or 0 here, which means I'm going to have horizontal. So anytime my x is 0, and that's why I do the undefined first. Because sometimes undefined and 0, undefined trumps everything. Not like, it's not political. No. Okay? It's not what I meant. Look at, you can't even use that word anymore. What the heck? Okay? Okay. Now, what do you think I should look at next? Well, x divided by y is my differential equation, right? What happens if x and y are equal? Then we're going to get 1. So if x equals y, that means our dy dx equals 1. And that's true whether they're both positive or they're both negative, correct? Which means 1 here, because 1, 1. At 2, 2, they're 1. At -1, -1, they're the same. At -2, -2, also the same. What happens if they're the same and one is positive and one is negative? It's going to be -1, right? So if they're the same and one is positive, one negative, one. Same here, same here, same here. What the heck is going on? Okay. And that leaves me some other points now I have to start to think about. Okay. So these I'm going to kind of do by plugging in and determining. So let's start with this one. A -1, positive 2. So if I plug a -1 and a positive 2, I get a negative half, right? Which means it's steeper. I'm sorry, it's shallower. How about a -2, positive 1? That would be -2. That would be more steep. I'm not even putting them on the marks. Positive 1, positive 2? That point? Half? And that one would be. So they're starting to mimic, aren't they? Okay. There is a pattern, guys, because there's a relationship between x and y, so of course there's a pattern. Okay? -2, -1. That would be a positive 2. It's going to be steeper. All right, let's start shallower. It does look cool. Some of them look really interesting, in fact. Okay, the more complex the derivative, the crazier that can get. So that's kind of what our graph would look like. Okay, here's the thing that you need to put on your paper. Like you need to write these words on your paper and star by them. Okay, do something. When you're sketching your function, when sketching the function, not the slope, but the function. When sketching the function, never, underline that 3 times. That's how important this is. Never go through an undefined slope. Never go through an undefined slope. Never go through an undefined slope. Because once you do that, you have given slope to a point that really doesn't exist. Okay, so if it's undefined, don't go through it. Stop. Go to it and stop. Okay, so the point that we're going to indicate here is 1, -1. Can anybody tell me what kind of function this would be? Probably not. It is not a log. This is a square root function. Yes, it's a square root function of a quadratic. So we're gonna go what? 1, -1. So that's our point to go through. And all I'm doing is following my slopes. It's gonna flatten out. This is actually the graph of y equals the square root of x squared. You're like, well, isn't that just x? No. It's plus and minus x. Because this is square root. So plus minus. It's actually a little bit more steep than what we did. The c for this one particularly winds up being 0. Okay. Good? Make sense? So, welcome art. See, math is art. You know there is a famous famous artist that was a mathematician as well. Escher? Escher? MC Escher? I'm sure if you saw one of his paintings, you'd be like, oh. Escher, not Usher.
I know, I was like, no.
Escher.
I was like, what?
I'll have to bring some of his work.
Does that mean you realize what he did was wrong?
He did every art that he did is based on some mathematical pattern. Yeah. Most of his are like tessellations or reiterations, things like that. That was to show you guys when you guys wouldn't recognize it. Hopefully. Okay. A lot of times what you're doing is you're matching a function to, or a derivative to its slope field. So the first thing I look at is my slope field in terms of x, in terms of y, or in terms of both. So I look for consistency. Is there consistency up, down, left, or right for this one? So if I go down, are all my slopes the same? No. If I go across, are all my slopes the same?
No.
Which means this is in terms of x and y. Is there consistency left to right or up to down? Okay. Up to down? Oh yeah, there it is. So that means this is in terms of x only. So up, down is x. Okay? How about this one? In terms of y only. Right? So this is an easy one to kind of match up because this is in terms of x and y, isn't it? Which is the only slope field that's in terms of x and y. Isn't that what we said? Did anybody make a note as to what I said as I was saying it? Okay. This is x and y. This one was x only. And this one was y only. Which means if this is an x and y, that has to be a. That's a slope field. If this is a y only, that means c goes with this one. I'm going to give, tomorrow we'll do some practice on this, and I gave a multiple choice where we have to go a little bit deeper than just this. And we'll talk about that one as a class together. Good?